Okay, hi everybody. Thanks for sticking with it till the end of the day. My name is Jeff Denworth. I'm co-founder of Vast Data. Privileged to be here. Thank you, E4. Thank you, Cosimo, for having us. It's really special. This is my second year getting to speak, so it's starting to become a little bit of a tradition, and I hope to get to come next year. Okay, so today I wanted to talk a little bit about what we think is the future of data and data management for artificial intelligence systems. This is where Vast spends a lot of its time. And the slides aren't working, so I'm not sure what to do. There we go. Okay, here we go. So if you saw us talk maybe 1, 2, 3, 4, 5, even 7 years ago, oftentimes I'd use this picture to kind of articulate how we think about the future of infrastructure and how real-time systems really couldn't deal with the classic storage tiering paradigm that a lot of applications have to deal with as people think about saving money on storage. If I fast forward to 2025, I think about this more in the context of the entire AI stack and the entire data center stack that's required to build for new agentic and inferential systems. And so, this pyramid that we use to show massive consolidation and simplification opportunities is something that we will continue to show as we start to climb this hill to build something that is far more than a storage system for our customers around the world. Now, who are those customers? One of them is xAI. xAI is building out about 500,000 GPUs in Tennessee. The last data center they built was exclusively Vast and is something that we're very proud of. Very, very high performance infrastructure that challenges data systems. We're operating at nearly 100% uptime there. CoreWeave is another great example. In Italy, they haven't become a presence yet, but one of the largest GPU clouds in the world that is standardized on Vast for all of its training and for its inference infrastructure. But Vast does more than AI. We're very proud of a recent win that just was announced. One of the exascale HPC systems that are being deployed is at the Department of Energy in the United States at NERSC. But we're also very proud of the work that we do in Italy, not just in Italy, but around the world. This is a customer that we've worked with E4 for now a number of years, Cineca, where they're starting to build unified infrastructure across all of the different HPC and AI systems that they build. And this is an agenda that we've been working on with them to simplify and fortify the data management stack across all the different systems that they deploy and across all the different data centers that they have, which we think is a pretty unique story in and of itself. But I wanted to talk a little bit about the evolution that the market is going to go through over the next couple of years. We spend a lot of our time in training. I just showed you a few examples of some very, very large training centers. And in 2025, what we've realized is that most frontier models have now the ability and the capability to essentially power business logic through the form of inference. And so now that the R&D, the research and development is done, people are taking these models and applying them to real automation and real capability that you can start to deploy and intelligence that you can start to deploy within your organizations. Now, in order to make this jump and in order to cross this chasm, a lot of the classic HPC mentality needs to kind of go away because the needs of tomorrow's AI inference infrastructure are not going to be similar to classic HPC workloads. First is they're not batch. You can't schedule when a researcher or a user will write a prompt within a system and say, I have a question that needs to be asked. You can't schedule when an agentic system needs to make some decisions on some external event that happens around the world. And so now you have infrastructure that needs to be operating at 100% uptime, which is a completely different mind shift from how most people have built HPC infrastructure. Number two is, in the training space, typically we've been conditioned to think that file systems are the way that you build training infrastructure. Well, reasoning agents, when they make decisions on how to action on something, they don't just look for file systems and well-organized training data sets. They just want to go and ask questions to resources that might be a data warehouse. It might be a file system. It might be some SaaS service. It might be the internet. And so now you have all these new data modalities that need to be accounted for as people start to build real AI scale infrastructure. And then the final point is you don't get out of training. Rather, training becomes a subcomponent of inference where this loop of continuous fine-tuning and training continue to run. So VAST stands in 2025 in a pretty interesting position. We built, I think of as carrier-grade or internet-grade, scalable, reliable infrastructure. And we're powering some of the world's largest data centers with 100% uptime. So we can support the needs of these inference workloads. We're the only system in the world that combines an enterprise parallel transactional data warehouse with a file system and an object storage system and a vector database, so customers have one unified data plane for all of their classic legacy data, as well as their new AI data or their new AI workloads that may want to process on legacy classic data. And the third is you get all these enterprise capabilities that are typically only associated with the legacy enterprise storage companies and database companies, but with the scale and the performance that you'd otherwise need for at-scale training. Now, how do we think about scalability? You could argue that Jensen both makes the Kool-Aid, which is a drink in the United States, I don't know if this resonates, makes the juice, and then drinks it himself, right? And so NVIDIA is now in the process of deploying something in the order of 100 million agents across their business. At 100 million agents, they're at 2,000 to 1 agent to employee ratio that they're going to be needing to build towards. And so if you think about this and the impact this would have on your business, you roughly have about, our estimation is about 250 agents per B200 class GPU. A company of 10,000 people would need roughly 10,000 GPUs to power its automation. Now, if that happens, the world will embark upon the most significant technology refresh event in history. The processors are all new from NVIDIA. The workloads are all new, inference and agents, but the data is all pre-existing and sitting in systems that are not ready for this level of computing. And that's where we come in. Okay, so VAST is one of the hotter companies in the space. Forbes just announced that we were the 24th hottest private company in the world in what they call the Cloud 100. We sit alongside AI leaders like OpenAI and Anthropic and Databricks and organizations like this. Our job is to transform data into action, and we do that by being far more than a storage system, which most people know is our history, but is definitely not only our future. And we do that through a new architecture that we've enabled that really changes the way that people think about scaling and uptime as it relates to all of their data requirements. Forbes also announced that we were part of the AI 50, the hottest companies in the world. We down-selected the 50. These are mostly model builders, a few infrastructure players. But if you take a step back and you look at our influence in this market, it turns out that a lot of the other organizations that were nominated on this list are also powered by VAST, which is something that we're very proud of. And so we built this company that is not 10 years old yet, and I like that because I like the soul of a startup. We are 1,100 people around the world. We're building a generational company. If you see about us in the news, we're really breaking all of the benchmarks that you find people measure companies like ours with. And the way that we do it is by rethinking the classic definition of distributed systems. When we started the company, what we realized is that the way that people built systems up until VAST was using an architecture that was largely popularized by Google back in 2003. Google put a white paper out, the Google file system. They said, this is how you build scale out. And what we think is that Google missed a few key things. The first is, at that time, nobody was really thinking about building low-cost flash systems. So everybody was thinking about tiers of infrastructure to balance either performance or capacity. At the time, networks were much slower than servers. And so people would put their data into their processors or put processors into their data so that you didn't have to move data around the networks. And so what came of that is rigid node definitions, where you have CPUs and you have storage devices, and you can't change these once they're created. But the big problem is the architecture created a lot of internal traffic as you manage updates or transactions or whatever between different systems. And so that works at relatively low scale. But as I start to scale up systems, what gets created is a quadratically larger amount of internal traffic versus external traffic at scale. And so that's why these technologies start to basically fall over at scale. And this is something that we solved with the implementation of a new type of systems architecture. We think we're carrying forward the work that Google did. Database and storage companies come in and out of the market fairly regularly. Only on a generational basis are new architectures invented, and we think we've invented the first new one since 2003. We call it DAYS. It stands for disaggregated and shared everything. And so a DAYS cluster looks like this. You take a bunch of commodity processors, they run software in Linux containers. Think about these as file servers, database servers, storage controllers, even a Lambda environment that you could just run a runtime in, just in a simple Linux machine. And then on the other side of the network, you have SSDs and new data structures that we created such that all of the SSDs basically just present one global volume. There's no notion of partitions, or you don't have to break a namespace up into multiple chunks. You can have all the CPUs in a cluster see all of the volume as just one big global volume, and they all know how to transact in and out of the machine. And so what comes of that is there is no east-west traffic. There's no internal communication between nodes in our system. It's, I would argue, the first truly implementation of a parallel file system and parallel database that's ever been invented. And we can do that because of a next-generation fabric that interconnects everything that largely came from NVIDIA. It's called NVMe over Fabrics, which you can layer over standard Ethernet or InfiniBand. So what do I get with this? Number one is I get a system that I can scale linearly. Today we're being deployed in the largest AI computing centers and the largest HPC data centers, and customers just notice the thing just scales. Number two, I get real time at any scale. The problem with transaction management across that shared nothing architecture is it basically means any scalable system isn't good for updates. That's why you have to deploy, for example, a Kafka cluster next to a data lake, because never have these two been mixed together. We've solved that with this new architecture. Number three is extremely resilient. Our customers operate at nearly 100% uptime. Take any of these machines, shoot them with a gun or hit them with a hammer, do whatever you want to do, and the system just stays online. And so this is a thing that I think in particular at scale becomes really, really important. And then number four, if I go back to that first slide that I showed, and basically talk about how our customers look to basically consolidate all their tiers with a bunch of new innovation that we've created around making storage more efficient, you can have one tier of flash for all of your data. Okay. So fast forward to 2025, as I mentioned, we're moving the pole, and we're basically showing people that this can be far more than a distributed storage system. That architecture I just showed you is basically a blueprint for a web-scale computer in software. Its first application was to do things like serve files and serve objects to applications, but now it's so much more. The vast database is essentially, if I think about an AI pipeline, you have, if I take the Jensen story where you have AlexNet that showed people how to run a cat video through a neural network and understand that there's a cat coming out of that. We've always believed that you need to build systems that can hold both the context in the form of additional metadata that can be queried with SQL, as well as the data in one unified system. And so with that, we created a data storage system that is now the most successful new startup product in history. And we're coupling that with a database system that you can write to as fast as you could write to the world's fastest streaming engine, and then query from faster than you can query from the world's fastest data warehouse. And so with that, we wanted to basically make it possible for real-time AI to contextualize data and then action on data. And if you don't have real-time, then you don't have real-time AI. And so with that, we added support for vectors, which are critical for generative AI data access, critical for RAG processes, and now we have a full-stack data layer for pretty much everything that an organization wanted to do with their AI initiatives. And then the compute layer has come in this year. We have 3 pipelines that we run in the platform natively that basically will transform your data from wherever data source all the way to something where you can use AI tools to contextualize your data, and then deploy applications and agents natively from the system as just one unified platform. So you have a runtime, you have an event scheduler, you have all the database services that you need, all the storage services that you need, and we take our architecture all the way down to bare metal. And if I look at that and say, okay, we've got even the device drivers, and I take it all the way up, we didn't know what to call this other than an operating system. an operating system for the era of AI, and one that you can deploy agents upon. So you can now consume this infrastructure from pretty much any of the major server vendors. We also have different reference architectures that we deploy with our logo on them. Customers can choose what they want. You can deploy VAST in the cloud as well. And as I mentioned, one of the objectives is to make things cheap. We want the world to be able to process indiscriminately on all of its data. And so the first step was to unlock that data by putting it all on real-time infrastructure. We're in Italy, where the cost of power is not free. And what we've determined through some recent analysis is that just from a power savings perspective, the things that we're doing with Flash make it possible to move away from hard drives absolutely. And there is no economic argument for hard drives anymore, particularly in high power cost geos. And so, so things get really interesting now that I can afford all Flash for all my data. We take that and we basically now can federate all of a customer's data centers into one unified data plane and also one unified computing plane. So you can actually use least cost routing to say, okay, if I have free resources here, maybe I move data there so that I can just do computing. Or maybe if I have a job that I don't care about, maybe I can move the compute to the data and wait till the resources are available. So you can basically optimize for time or money with one unified and consistent and high-performance system. We call this the data space. And so we've been working to basically very, very quickly build in new capability into systems that no organization in the world has ever seen from a single software stack, from a single product. And this is a journey that we've been working on since 2016. And I just wanted to give you a preview of what we think data infrastructure of tomorrow will be. Imagine you have pipelines where you basically just have all sorts of data streams coming in, either to unstructured data systems or structured data systems. In the case where the data is unstructured, meaning I don't understand what's inside of it, now you can use new tools to basically extract and embed information from these using AI microservices, and then put those into a real-time vector database that can be made available to either an LLM or to an agent. There's all sorts of new things that we have to learn now with respect to AI inference deployment around something called MCPs. It stands for Model Context Protocol. MCPs are how agents work with each other, and more importantly, how they access resources to do their tasks. And we have a full MCP server layer that sits in the system that basically feeds these agents with the information and the tools that they need. And so if I look at this entirely, we kind of think about this as the modern OS for AI pipelines. And we're building in all sorts of infrastructure into the platform so you can just run your code natively from within it. There's a serverless layer. You can just program everything with Lambdas. There's an event broker. And then all the state kind of sits in the system. And as events happen, as files hit the system, then they just call functions that will run across Kubernetes pods. And so we think a lot about where does this go, to what end? And a lot of the work happening right now in the AI space is around taking enterprise data and contextualizing it and indexing it for AI access. That's a process called vectorization. And most vector databases weren't designed for scale. Most vectorized or RAG projects are not necessarily so popular right now because people think that it's really hard to get your data curated in a way that you can basically trust an AI engine to deal with that data in an indexed and proper fashion. But I think we're pretty limited in our thinking on this because over the next few years, you're going to have AI intelligence that will either be equivalent to or will exceed what a standard data engineer can do. And at that point, once GPUs can just curate your data, you're going to vectorize everything. So we play it forward and we talk about where the world is going. And once an average organization with 50 or 100 petabytes realizes that they need to feed all of this data to their AI engines, then you have a vector problem. A vector problem that is far greater than any vector database was ever designed to support. We're envisioning a world where customers have trillions of vectors in their environment. And we wanted to build a system that allowed for you to kind of build a vector space, which we think of as metadata on top of data, in a very scalable way, with the ability to search from that in constant time, regardless of how large the vector space is, We wanted to be able to insert so that as new data comes into the system, it can immediately be vectorized and made available for whatever business logic that you have. And then, of course, it needs to be secure. And security is fundamental. And by bringing a vector database into the source data system, then you have one security model for all of your data. And so what we built is this basically new ETL pipeline that runs within the system that takes unstructured data and turns it into something that has structure. People use the term unstructured data. I don't think we will be using these terms anymore in the future just because everything's understandable thanks to AI and thanks to inference microservices. And so I'm going to fast forward through this. So imagine all of your data can just be run through these types of routines automatically and programmatically. I wanted to give you all just a preview of how this looks at scale. And so the cool thing is that it's completely embedded into your data source, which means that you have no separate ACL cache or separate permission systems for your metadata as well as your data. It's all one unified system with one unified set of access policies. And then if I take that and say, okay, let's start to build on this system. Well, one of the things that we do is we give a few examples. You can take, for example, a bunch of collateral that an organization may be sitting on and say, okay, I'm going to create some resources for my sales team. So I'm going to create what's called a RAG, or a Retrieval Augmented Generative AI tool, that looks at all of an organization's, let's say, slides and documents and videos, and basically, very simply, decides on how those data objects get processed and then fed through a pipeline where everything becomes expressed as a vector. So this is taking a little longer than it normally does. But yeah, so let's say I take all of this, I run it through a deduplication function, I run it through a sensitive data reduction function, and then I basically just create vectors on it. All of this is now capable to be done automatically within your system, so you can basically make all of your data AI ready. And there's tools that, in particular, NVIDIA ships that make it possible to kind of do this at different levels of scale for different data types, and they keep adding more data types on a daily basis. Now, once you have this, the question is, well, what do I do with this new contextualized data? Agents become the natural thing. Agents can reason on and think through complex topics that you ask questions about, or other automatic systems may ask questions about. And so we built into the platform all of the ability to basically auto-scale agents within the system with fault tolerance, with tracing, with security personas, and a low-code environment that allows you to very simply build agents using tools. So let's take that pipeline that I just created, that RAG pipeline that basically contextualizes sales and marketing data, and I'm going to deploy it as an MCP tool, a Model Context Protocol compatible tool that any agent can access and use as a resource as its reasoning. Well, with that, you basically have this now toolbox that you can feed to different agents. So I'm going to create an agent. It's going to have a unique name. It's going to have its purpose. It's going to have some reasoning models that you couple it with. Let's say that's DeepSeek or any others that you choose. And with that, I then go couple the tools that you use to the agents that you create, and you have pipelines built into a very simple and secure and unified system with simple and unified observability. So the future of data infrastructure is far beyond just POSIX mount points and S3 buckets, and we would welcome everybody to talk with us about where we think things are going. We just did this very large project in Asia where customers realized that you could take agents, reasoning agents, and apply them to things like video surveillance and get a far greater understanding of the context and the dimensions of a scene than what you could find within a classic a way of approaching like yesterday's perception-based AI tools. So we're really excited about it, and we hope you come talk to us. And thank you for your time.